Welcome to the Visualizations of Model Performance tutorial. My name is Joel. I'm a senior at Purdue University studying biological engineering, and I'm an undergraduate researcher with the Purdue Data Mine working alongside the Lawrence Livermore National Lab. In this session, we're going to explore some of the amazing tools provided by AMPL to visualize how your model is performing through its training process. We'll walk through some key visualizations that help us understand not just the final results, but how our model improves over time. These tools give us a peek into the training process, which is crucial for understanding how well the model is learning from the data. Some of the tools we use in this tutorial are specific to certain types of models, so don't worry if a tool doesn't apply to all the models you may work with. Let's start by taking a look at the functions we'll be working with today. Plot perf versus epoch is used to track how the performance changes as we train. Plot pred versus actual shows how our predictions match the actual values. Plot confusion matrices is used to understand misclassifications in a classification model. Plot model metrics is used for an overview of important model statistics. Plot ROC curve is a great tool for evaluating classification models, and plot precision recall curve is used to assess precision and recall trade-offs. We'll be using the same dataset and scaffold split from tutorial 3, train a simple regression model, to create a neural network model and visualize how they train. Later on, we'll convert our dataset into a binary classification one, so we can train classification models and use some of those specific visualization tools. Alright, let's get started by importing some standard packages and modules we need for analysis. These imports are essential for handling data and for visualizations. Here's the code you'll be running to get everything set up. We'll start by importing basic libraries like pandas and numpy, which are used for data manipulation and calculation. We'll also import JSON for handling data in JSON form. Next, we'll set up logging to avoid unnecessary chatty log messages while we work. This makes our output cleaner. Now that we have our libraries ready, let's move on to the fun part, the model training. We'll train a simple, fully connected neural network model. This model will take in our dataset, which contains information about chemical compounds, and try to predict their activity. We'll be using the SLC683 dataset in this case. In AMPL, when you train a model, it goes through several iterations or epochs. At the end of each epoch, it evaluates how well it performs, and this feedback helps us improve with each pass. So, in a neural network model, you have an input layer, and information is passed through multiple hidden layers to the output layer. And through each epoch, it returns to the input layer, switches some parameters around, and continues training. Here's what's happening in the code. We define the dataset file path, set up some basic information like the response column, what we're trying to predict, and specify the split UUID to tell AMPL how to split the data into training, validation, and test sets. When training models, we often don't want to run forever. This is where early stopping comes in. With early stopping, the model will halt if the performance on the validation set doesn't improve after a set number of epochs. This helps us prevent overfitting where the model becomes too tuned to the training data and fails to generalize well to new data. The early stopping in this case is set to 20 epochs. Now that we have everything set up, we're ready to start training our model. As the model trains, AMPL will save performance metric after each epoch, like RMSE or root mean squared error, which we'll be using to track performance alongside the default R-squared score. Root mean squared error begins with the actual value in y sub I and the predicted value in y hat sub I. The difference is taken, and this is squared, divided by the total number of values. This is then square rooted. The root mean squared error gives a good explanation of how closely related the predicted and actual values of a dataset are. Once the model is trained, we'll be able to use these performance metrics to generate visualizations, like how the model improves over time and where it might be overfitting. Now that we've got our dataset and parameters in place, let's dive into the process of featureization and training our model. Featureization refers to the transforming of raw data into a format that our model can process. Essentially, we're taking chemical data, like molecular structures, and converting them into numerical descriptors, or features that describe each compound's properties. In the case of our dataset, we're using a predefined featureizer called computed descriptors from the RDKit library, which gives us a set of descriptors for each compound. These descriptors are like the fingerprints for each molecule, capturing important features about its structure and behavior. Here's where we define the featureization parameter. In the descriptor type, we're using RDKit raw. In the model type, we're working with a neural network model defined as NN. In prediction type, since we're predicting continuous values, this will be a regression task. Once these parameters are set, we'll create a pipeline with model pipeline, which orchestrates the entire performance of training our model, starting from the dataset, applying the featurizer, and then moving to the model training. In the next block of code, we kick off training with this regression pipeline train model. The model training process begins, and AMPL will iterate through multiple epochs or training cycles as it progresses. It evaluates and logs the performance of the model on the training, validation, and test sets. For each epoch, we see the following. The R-squared score. This value measures how well the model is fitting the data. The closer it is to 1, the better the model. We'll also track performance across training, validation, and test datasets. Now, let's visualize how the model performance improves with epochs. By the time we're done training, we should have a good sense of how well the model is generalizing to unseen data and whether it's starting to overfit to the training data. Here's a handy function that we'll use to plot the performance across epochs. We'll call it using the plot performance versus epoch and give it the regression pipeline. This will give us a plot of performance metrics across epochs showing how the training, validation, and test scores change. The goal here is to see the training score improve steadily while the validation and test scores should rise and level off, ideally without dropping, which would indicate overfitting. Let's walk through what we can expect. At the start, the model's performance is low, and the R-squared score for training, validation, and test sets are all near 0. As you go through the epochs, the model begins to learn from the data. The R-squared score increases as it improves on both the training and validation datasets. You'll notice the model's performance on the training data usually improves faster than on the validation or test datasets. This is normal as the model is memorizing data it sees during training. If the model continues to improve on the training set but fails to show the same improvement on the validation or test set, it's a sign of overfitting. One of the great features of this process is the early stopping mechanism. This helps prevent overfitting and saves computational resources. At the end of the training process, we have trained a model ready for predictions. And with visualizations, we can understand how the model learned and where it can improve. Next, take a look at this vertical dashed line on this plot of negative RMSE versus epoch. This marks the epoch where the validation set's RMSE was at its lowest. Why is this important? Well, the parameters from that checkpoint file, the one corresponding to the minimum RMSE, are what gets saved to the final model file. This helps us capture the best version of that model. It's also worth noting, if you're optimizing for a different score, like R-squared score, you'll only see the plot on the left. In some cases, the epoch with the best R-squared score might not align with the one that minimizes RMSE, so always check the results carefully. Sometimes looking at one number, like R-squared score or RMSE, doesn't give the full picture of how well the model is performing. This is where the plots of prediction versus actual function comes in. This scatter plot compares the predicted value against the actual value for each split subset of your data. It helps you see where the model is excelling and where it may be making mistakes, giving you clues on where improvements can be made. In this particular dataset, there's an interesting feature. Notice how we have a vertical line of points with the actual value of 5. These represent sensor data where the Ki values were reported as greater than a certain threshold because higher values couldn't be measured precisely with the maximum concentration tested. This is a common experimental setting where the measurement tool has a limit. From the plot, we can also see that higher Ki values tend to be underpredicted while lower Ki values are overpredicted. This gives us a valuable insight into where the model could use some tweaks. Perhaps a deeper dive into hyperparameter optimization is needed. If you're working with the previously saved model, don't worry. You can still analyze the performance using plot prediction versus actual from file. The function works with saved models, unlike the one we used before, which only works with the model trained in the current Python session. Let's test it on the best random forest model we saved from a previous tutorial on hyperparameter optimization. As you can see, now we're loading a saved model in its corresponding dataset. We're using the dynamic featurization in this case, meaning we're working with ECFP features. These features describe the structure of the molecule in a way that's useful for machine learning. After featurizing the data and transforming it, we can evaluate how well the saved model performs on the dataset. Now with this comparison, you can see how well the saved model's predictions align with the actual values. These visualizations offer a clear, easy-to-interpret way to understand model performance and highlight areas where further improvements can be made. Now that we've looked at visual performance indicators, the next step will be to dive into improving model accuracy and making sure our predictions are as reliable as possible. In this next part, we'll be diving into how to evaluate the performance of classification models, which are designed to predict discrete classes. For example, a model could be predicting whether a compound is active or inactive based on its structure. The evaluation of classification models involves different performance metrics compared to regression models, and we'll explore some unique visualizations that AMPL provides for this. But first, let's create a binary classification dataset. The dataset will be based on the SLC 683 Ki dataset, which contains information about compounds. For our binary classification, we'll assign a value of 1 to a compound with a pKi greater than 8, which means they're considered active, and 0 for all other compounds, and those will be considered inactive. Here's how we'll be doing that. As you can see in the code, we're reading in the dataset and adding an active column and saving the updated dataset. This result will tell us how many active and inactive compounds we have. This creates an imbalanced dataset. We have more inactive compounds than active ones, which is quite common in real-world datasets. But don't worry, we can handle this imbalance with AMPL's tools, which we'll get to in a moment. Next, we'll split this dataset based on the scaffold of the compounds, which means we group similar compounds together. Here's the code for that. What we're doing here is telling AMPL to split our dataset into training, validation, and test subsets. It's good practice to ensure that the class proportions, active versus inactive, are similar across training, validation, and test sets, especially with imbalanced data. So we can use a visualization tool for AMPL to do just that. Let's take a look. This plot shows us how well the active compounds are distributed across the different subsets. We're looking to ensure that the proportions of active and inactive compounds are balanced. And this looks good. Now we can move on to the training model using these split datasets. We'll use a neural network model to predict the class of compounds, whether it's inactive or active, using ECFP fingerprints. Here's the code for training. By setting these parameters, we're telling the model to interpret the dataset and where to save the results. So now that we've set up this dataset, split it properly, and prepared the model for training, let's move on to using ECFP, which stands for Extended Connectivity Fingerprints. This is a way of encoding molecular structures into numerical form that our model can understand. Once the data is ready, we'll proceed with training. We're using a neural network model composed of layers that process data, and we'll define the size of these layers as well as the dropout rate, which is a technique used to avoid overfitting by randomly ignoring some neurons in training. The learning rate controls how quickly the model updates based on new information, while epochs define how many times the model will go through the training data. The next part of the script focuses on training the model with actual data. During each epoch, the model's ROC-AUC score is calculated, which stands for Receiver Operating Characteristic Area Under the Curve. This is a measure of how well the model distinguishes between different classes. This image shows a Receiver Operating Curve, or ROC curve, a graphical representation of a classifier's performance across different thresholds. The x-axis represents the false positive rate, and the y-axis represents the true positive rate. The red dashed diagonal line represents a random classifier indicating no predictive power, and this performance is equal to random chance. The blue curve represents an ROC of a perfect classifier, which achieves a true positive rate of 1 and a false positive rate of 0, meaning perfect predictions. The green and orange curves show better and worse classifier performance compared to random guessing. The distance between the ROC curve and the diagonal line indicates the classifier's performance. A larger distance indicates better discriminative power. This visual is commonly used to evaluate and compare machine learning models based on their ability to differentiate between positive and negative classes. So now you can see a high true positive rate with a low false positive rate indicates a better performing model. And as you increase the false positive rate with a lower true positive rate, then you have the random classifier. Lastly, we visualize the model's performance over the training epochs. This is done using the function plot performance versus epochs. This helps us see the improvements and identify the point where the model stops getting better. Now that we've seen the ROC-AUC curve, it's important to dive a bit deeper into the performance of our model. The ROC curve reaches about a 0.88 at 13 epochs, which sounds pretty good, right? But here's where we need to be cautious. Our dataset is highly imbalanced, meaning that there are more inactive compounds, 1,597, than active ones, only 222. To put it in other terms, imagine you are trying to guess whether an MRI scan depicted evidence of cancer or not. If every time you predicted that a scan did not show cancer because you knew that an absence of cancer is the majority of scans, let's say 99.9% of the time, your guess would be right 99.9% of the time, which is a very high accuracy. But that doesn't mean you're predicting anything useful if you're just predicting no cancer all the time. You'll miss all the cases of cancer, and in this scenario, that's not an option. This is what is happening here. Our model might be doing well on the ROC-AUC, but it might just be learning to predict the majority class, inactive compounds, in this case, all the time. Now let's take a closer look at the performance using other metrics. These will help us understand how well the model is truly identifying the active compounds. Let's visualize a confusion matrix. This is a tool that helps us understand exactly where the model is making mistakes by comparing predicted versus actual values. You can think of it as a map of sorts. It shows how many of the compounds the model correctly predicted as inactive and active and how many it got wrong. To do this, we use plot confusion matrices. What we see here is a table structure that splits the predictions into 4 categories. True positive. These are active compounds that were correctly predicted as active. As you can see, true has a 1 and predicted has a 1. True negative. These are inactive compounds that were correctly predicted as negative. These are the 0, 0. False positive. These are inactive compounds that were wrongly predicted as active. And a false negative. These are active compounds that were wrongly predicted as inactive. So the true class would be active, but we predicted 0 or inactive. A more basic form of this would be you have a predicted class and a true class. And for the predicted class, you have a negative and positive, and for the true class, you also have a positive and negative. If the positive and positives match, you have a true positive. If the negatives and negatives match, you have a true negative. And the opposites are a false positive and a false negative. From these confusion matrices, we can see that our model is doing much better at predicting the inactive compounds, but it's not helping us find those elusive active compounds. To help us out, we can dig into precision and recall metrics. These are critical, especially for unbalanced datasets. Precision tells us how many of the predicted actives are actually active. As you can see, it's true positive over all of the predicted class positives. High precision means that the model isn't making many false positive errors. Recall, on the other hand, tells us how many of the actual actives were predicted by the model. High recall means that the model is doing a good job identifying active compounds, but if the recall is low, it's missing many of them. For our unbalanced dataset, precision and recall give us much more insight into how the model is performing compared to accuracy or ROC-AUC. Let's plot these metrics for each subset using the plot model metrics function. Looking at the results, you'll notice that while accuracy is hovering around 90%, the precision is 100%, meaning all the predicted actives are indeed active. However, the recall is only around 21%, which tells us that out of all the actual active compounds, only about 1 in 5 are correctly being identified by the model. This discrepancy shows us that while our model is being cautious by predicting only the most certain cases as active, it's failing to identify many of the true actives. This is a classic example of the challenges that come with an unbalanced dataset. Now that we've seen the performance of our initial model, let's talk about how we can improve it. Specifically, we want to focus on boosting the recall without sacrificing precision too much. To address this, we'll tweak a model parameter called model's choice score type. Instead of using the default metric ROC-AUC, we'll switch the metric to one that balances precision and recall. Two popular choices for this are balanced accuracy and Matthews correlation coefficient, or MCC. For this experiment, we'll use the MCC as it's especially good with an unbalanced dataset. Let's dive into the code. Here, we define the parameters and update the model choice score type to MCC. We'll keep the rest of the parameters the same as before. When we run this, the model will now focus on optimizing the MCC. Let's plot the performance and compare it to what we had earlier. We use a bar plot, the same as we had before, to evaluate the precision, recall, and accuracy. With the MCC-driven model, the goal is to have a better recall while not dramatically reducing precision. This is a great strategy, especially in cases where missing out on true positives, active compounds, in our case, could be more costly than a slight reduction in precision. You'll notice that recall has improved slightly from 0.2 to 0.3. Recall is all about minimizing the chance to overlook a positive case. On the flip side, precision has dropped from a perfect 1.0 to around a 0.6 here, meaning we're more likely to have some false positives, compounds that are predicted as active but they actually aren't. But here's the key point. Whether this is acceptable depends entirely on your goals. Are you more concerned about missing a potentially valuable drug, or is it more important to avoid wasting resources on compounds that aren't really effective? It all depends on you. This is where the flexibility of AMPL's selection metrics come into play. By adjusting parameters and focusing on metrics like recall or precision, we can shape the training process to match your priorities. At this point, you've learned the basics of how to tweak your training strategy to balance between recall and precision, as well as how to use different metrics for optimization. Next, let's dive into the weight transform type parameter and how it can help us with unbalanced datasets. In classification problems, especially when you have an uneven distribution, the model will often have a bias toward predicting the majority class. This is where the weight transform type comes in. Specifically, setting this parameter to balancing adjusts the way the model evaluates the training data by giving more importance to the minority class during the learning process. This works by changing the cost function, which is essentially the model's way of measuring how well it's performing. By giving higher weights to the minority class, the model is penalized more for misclassifying these minority examples, making it more likely to pay attention to those underrepresented cases. For example, in drug discovery, if we have far fewer active compounds than inactive ones in our dataset, a model without this adjustment might simply predict inactive for almost everything. But with weight transforming types set to balancing, this model can learn to predict active more often, improving its overall performance. Let's move on to how this interacts with another parameter, the model choice score type. By combining balancing with a suitable score type like MCC, we can better handle the trade-off between precision and recall, depending on the task's need. Once a model is trained, we'll now look at our bar plots. As we can see, with our MCC and balancing, precision is sacrificed a little bit more, but recall is increased. We can also take a look at the model's performance metrics. Which just shows the numbers corresponding to the bar plot results from above. Next, let's visualize our model's performance with the ROC curve. As I said before, it plots the true positive rate against the false positive rate by varying a threshold. With just this line of code, we can generate the ROC curve for our model. AMPL plots the ROC curve for the training, validation, and test sets on the same graph, making it easy to compare them. This model falls in the good to better category as it hangs close to the top left corner. The AUC helps categorize the best model into a single number instead of looking at how close it is to the top left corner. It stands for area under the curve, and so a model closer to the top left corner will have a higher area under the curve. Next, we'll look at precision recall curves. This curve is especially useful for when you're working with imbalanced datasets. Here's an example of a generalized precision recall curve. As the recall is varied, a no-skill model will have 0 precision, and as the model goes closer to the top right, the precision increase will also have a very high recall. A good model, one that cannot reach the perfect status, will have some sort of trade-off between precision at different levels of recall. AMPL computes the area under this curve, also known as the average precision, or AP. This is similar to the AUC from the ROC curve. The higher AP indicates a better model performance. For our model, the train is close to a good model, while the validation and test sets are closer to a worse model. And that brings us to the end of our tutorial series, highlighting the core functions of the ATOM modeling pipeline, or AMPL. Thank you for sticking with us for all 8 of these tutorials. We hope you found them helpful in learning how to evaluate and apply your own models for predicting chemical properties. If you have specific feedback or suggestions about the tutorial, we'd love to hear from you. Please take a moment to fill out the AMPL tutorial evaluation so we can continue to improve and make these resources even more useful. Now that you have the foundational knowledge of AMPL, I encourage you to dive deeper, explore different datasets, read through the documentation, and engage with the wider community. I'm excited to see how you'll apply these insights, and I look forward to the discoveries you'll make along the way. Remember, like machine learning itself, our journey in mastering these tools is ongoing, filled with learning, experimenting, and evolving. We break up challenges, iterate to grow, and optimize for better outcomes, just like these models do. Machine learning isn't just a tool. It's a reflection of how we continuously refine ourselves to impact the world around us. Thank you for watching.